Hello. Welcome to another B stream. So this week we're going to be talking about the storage layer and how we persist information about the state of the tangle and things like that. In the call today, we have Alex. We have myself. We have Loué, and we have Thibaut. So hello to everybody in the chat. We've got an echo. You say? That's strange. Is it still echoing? No response in the chat. Okay. Well, I'm gonna assume it's okay at the moment. Oh, right. The echo's still there. What's it coming from? I'm sure we had this last time. That is strange. Only certain people are hearing it. Is it too bad for me to continue? Okay. So, right, I've turned off the internal audio source. That gets rid of the echo. So presumably then, okay, how's that? Hopefully the echo's gone now. Okay. Well, let's hope that stays working. So now that I've wasted 5 minutes playing around with audio, let's actually get into the meat of what we're talking about. So with the B node, we connect to the wider network. We start to sync ourselves with the network. But it's quite useful to not need to synchronize the entire history of the tangle. So for that reason, we persist certain information or certain pieces of information about the tangle. So a history of transactions and things like that. So we do this. Have we still got an issue?
But the echo is back and it's back and you're not.
Right. I might have to just turn you off then, because I have no idea what's causing this. Okay, I've turned off the call, so hopefully that's fine now. Okay, right. So the storage layer is going to be storing information about the tangle, so a history of transactions and how they reference one another. So we have a variety of types that we need to persist about the tangle. So things like ledger information, transactions, and milestones, and there are a few other things. Okay. So I'm using this B something name here to represent most of the crates in the B ecosystem. So these are all crates with types that we want to persist in storage. And then we have the storage crate, which actually implements all of the storage layer. And we want these two things to talk. So we want to be able to persist these types here and persist them in the storage. But we also want the option of having many different database backends. So for example, we want to store things using RocksDB or SQLS and so on. So yeah, what I'll do then is I'll try that. I'll try muting myself in the call. Hopefully that works, and hopefully the echo is still not back now. Is it all fine? Is it all fine? Okay, so muting myself in the call didn't work, unfortunately. It was worth a try. So back to the presentation. So we have all of these database backends that we want to potentially use. Okay, and we want each of them to understand how to talk to each of the types that we want to be persisting. So for that reason, we need a layer to communicate between them. But the problem is because we have lots of different types and lots of backends, we have this n times n style problem, which is where you're trying to implement a piece of code for two different combinations of two different independent variables, and you end up with a lot of different combinations that you need to implement the code for. And this is not really ideal because that's quite hard to maintain. You've got a lot of boilerplate code that's moving around, and if you want to edit it or change how a particular thing works, it means you've got to change all of the versions of them that do things in a certain way. And this is quite frustrating, to be honest, and it's something we'd like to avoid. So this turns out to be a similar problem to what the language server protocol solves. So the original problem is that you have lots of text editors and you have lots of programming languages, and you don't really want to be implementing tooling for every language for every text editor, because that's a lot of work. So say you have 30 text editors and you have 30 languages, then that's 900 different pieces of code you've got to implement in order to make all of them talk to all of the other ones. So what the language server protocol does is it turns this n times n problem into an n plus m problem. And it does this by creating an intermediate layer. So this layer is like a common interface that all of the languages can talk to and all of the editors can talk to. And this turns out to be quite a good way of solving the problem because it massively reduces the amount of code you've got to write. And it also means that a useful byproduct of it is that it forces you to think about the sensible way to design these things. Oh, is it? Am I viewing the wrong browser window? There. Right, so it allows you to solve this problem by creating a common interface between them. And we're going to try to do a similar thing with this problem in order to solve the problem of many databases and many types that we need to persist. So to do that, we've first got to have a grasp on what this interface might look like. And it turns out that there are certain common patterns between them. So for things like a ledger diff, a transaction, and a milestone, so all of these types that we need to persist, they make a lot of sense if we just turn them into a byte buffer. So we serialize them, and then we can treat them all the same. And this is quite useful because if we can treat them all the same, then we can use the same code to manipulate them. And it turns out that a lot of the access patterns that we use for accessing data in the database in B fit quite cleanly on top of a map pattern. So we have a key value, so for example a transaction hash, and then we have the value itself, which is the transaction. So we might refer to that transaction via its hash and use that to call it up from the database. So realizing that we can unify these designs is a first step to creating a system that talks between them. So we've come up with this system that has a set of common traits that are common to all of these things, and they provide a generic way to talk about, say a piece of data that wants to be persisted, or a database backend, a storage layer, effectively, and a way to talk, and also a way to talk about how we can map them together. So I'm going to sort of run through how we can use Rust's traits system in order to achieve this layer of abstraction. And we're going to do that in the Rust playground, which is just, you can write some Rust code on the web and run it and so on. I'm not actually going to be running it at the moment. I'm just going to be planning out the structure of how we represent all of these traits and abstract things. So the first let's change window again. Where are we? Hopefully you can all now see the Rust playground. So the first thing we're going to be doing is we're going to be creating these we're going to be creating these traits. So we're going to have a storage trait, and we're also going to have a data trait. My browser's being incredibly slow at the moment. I might actually switch over to another editor. Right, yeah, let's use this one. Let's save this somewhere. So we're going to create these two traits here. Let me just check the chat. Okay, so data is going to represent a thing that can be persisted, like a hash or a transaction, and storage is going to be representing a database backend. So there are a few things we need to do to tie them together. So the first one is we need to find a way to go between bytes and the piece of data itself. Okay, so we're going to have this method on data which is called Encode, and it's going to take a reference to self, and it's going to spit out some bytes, a vector of bytes. So this is all well and good, but there are a few problems here. Firstly, we might not want to be allocating an entire new vector for everything we persist. So we might want to persist only a number which could be represented as a few bytes, and we're going to want to avoid persisting that. So what we can do instead is we can pass in a mutable reference to a vector of bytes, and then just insert it into there, and this is a lot cheaper. The next thing we're going to want to do is to decode a series of bytes, so a slice of bytes, and turn it into an instance of that data again. But again, we've got a problem here because not all byte patterns might be valid representations of this type. So we need a way for this to fail. So a way for this to fail in Rust is to use the error type. But now we need to have a type here for this error. So a good thing to do would be to create an associated error type for the trait that allows us to have a unique error type for each of these types that we want to deserialize or serialize. So that's okay as initial implementation for data. So let's move on to storage. So there are a few things we want to do for storage. We're going to want a way to start the storage layer. So for example, we want to start up the database and get everything running at the start of the program. So we're going to want a method that creates an instance of the type. And that's great, but we may want to have a way to also configure it, because we might want to point to a particular file in memory that we use as the database, for example. So we're going to want to parameterize it with a configuration type, but the configuration types for each of our database backends are likely to be different. So again, associated types come to our rescue, and we can have a config type that's associated with this trait implementation. Are there any questions so far? Hopefully all good. Okay. So the next thing we're going to want to do is we're going to want a way to shut it down. So this, if anything, is even more important than starting it up, because correctly shutting a database down is the best way to make sure that you're not corrupting any of the data or so on. So we're going to want a shutdown method that consumes self. So consuming is a concept that's a bit unique to Rust, in that it means that we can take a value and have the compiler make sure that it's not used anywhere else again. And you can have a method that, when called, will consume itself, or rather consume the instance it's called on. And so this could potentially be a fallible operation, right? It could fail. So we want to have the result of this method be potentially an error. So just like previously, we can use an associated type, an associated error type, to allow a database backend to change its own error type. And similarly, we're going to want to do this for the startup as well, because startup may fail. It may be that the file doesn't exist, or something like that. So these are our fundamental types that we're going to use to try to tie all of this together. So the key thing here is that we want to codify the access patterns that we're going to be using for accessing data in the database. So I mentioned previously that the database acts as a key value store, and it does this by allowing us to access one item through another item. So for example, we might create this mapping trait, which allows us to define how one value might be mapped to another value. So for example, a hash might be mapped to the transaction that that hash is of. Did that make sense? The transaction of the hash. Or rather, a transaction's hash might be mapped to its transaction. So the way in Rust that you tie these things together, you associate them, is again with an associated type. And it turns out that associated types are really useful in Rust and used all over the place. So we have this key and value mapping here. Key is the thing we're using to access the value with, but we want to mandate that these two things are both kinds of data. So Rust allows us to do that by adding a trait constraint. So now we're requiring that they both implement the data trait. So the next thing to do is think about how we want to access items in the database. So a common access pattern you often see that I think is quite useful for now is often referred to as CRUD, or CRUD, which means create, read, update, and delete. So these are the 4 common actions you might want to perform on items in a database. So we're going to call them something slightly different. And update and create in our case are basically the same, because we're storing everything as effectively just a byte buffer. So we're going to have insert, and we're going to parameterize all of these methods with a mapping trait, or rather a mapping type. So, for example, we might have something like hash to transaction type, which maps hash to type transaction, and we might use this on our storage like this. To insert the transaction into the database. So let's write that method now. So the first thing we need is the key that we're inserting into the database. But this K here for key, it needs to refer to the key that's specified down here in the mapping type. So M is our type that implements mapping. So we're going to do M key, and the same for value, M value. And the thing it's going to do now is it's going to return a result. So insertion may inserting a transaction may fail, for example, because it might be that the transaction already exists, or there are other miscellaneous things wrong with it or wrong with the database. So we're going to want a way for that error to be propagated up again, because error handling is very important, of course. We're also going to want a way to delete, but in this case, we might not know the value we want to delete. We might only know the key. So with this one, we're going to pass in the key only. Next one we might want to do is to fetch from the database. So effectively read. I'm going to call it fetch just because to me it feels like a term that better embodies the act of taking something from the database without necessarily knowing what it is or how it works. So you can see here, we're taking the key of the thing we want to access, and we're returning its value, or we're returning an error. That's also another option, because of course all of these things are potentially can fail. Let me just check the chat. Yeah, so the store method on the storage is effectively what insert is. I think on a previous initial design of these traits, I actually called them load and store, which are more akin to the terminology for things like instructions, assembly instructions, that is. I'll probably end up renaming these at some point in the implementation, just because their naming feels a bit consistent, but I think it's okay for the purposes of this demonstration. So the next thing we're going to want to do is we're going to want to allow a database to provide some way of I've lost my train of thought. Yeah, so we're going to need a way for databases to customize the way that a certain mapping is accessed in the database. So for example, we might want to have a particular table that contains a mapping between a certain key and a certain value, and we want to specify the table that specifically we want to refer to. So a good way of doing this might be, again, to have the storage say, right, I'm going to have this mapping, let's call it mapping config type, and this type is going to tell me how to refer to a certain table in the database. So for example, in many cases it might just be a string, which is the name of the table you're accessing. And down in the mapping, where this mapping is defined, we're going to want to provide a way for that mapping to define which table it's mapped onto. So let's have a method like get mapping config, and it's going to return a type that implements, or rather it's going to return this type up here. But we've got a problem now, because this type isn't a concrete type, right? It's just saying there is a type that will at some point be defined that in this context we're going to call mapping config. But it doesn't exist anywhere here, right? It only exists in storage, which means that our mapping type is going to need to be parameterized by a storage type. And now we can refer to that storage's mapping config. So now what we're doing is we're binding together the key, the value, and the storage all into a single trait here, which you can think of the mapping as being the matrix part of the intersection between all of the databases and all of the types in B. And then we're going to move all of the n plus m stuff over into these traits in order to reduce the work we need to do when talking about the intersection between different types and different databases. Hi Pedrock, what are you referring to in particular? Are you just wondering what the live stream is about? So we're writing, we're planning out the architecture for a database backend and how that backend will attach to the higher level parts of the B node. So now that we've got this extra parameter on mapping, of course we need this parameter here. So in this case, we want the mapping to refer to the current storage, so self. So we're going to add that parameter to all of these. Because we're referring to self in a lot of these methods in a way that when the compiler compiles the code, it requires these things to have a known size in order to fit on the stack and be passed as parameters to methods. What we're going to do is we're just going to add a sized constraint on each of these types, or rather on each of these traits, except not on this one, because we currently don't refer to itself within the trait. So the next thing that we can do, you just jog my memory a moment, which check the chat at the same time. If anyone's got any questions, then feel free to ask them. So the next thing that we're going to want to do is when you have a certain type you want to decode from some bytes, a certain piece of data, you don't always know what size it is. So for example, you might have just something like an integer that always takes up 8 bytes or whatever, and that's all fine. But there are times when you might have a thing that takes up many bytes. So we're going to provide a way for the thing that's being decoded to say, hey, I've only taken up these bytes, and now you can use the rest for decoding things. So we're going to do this by passing back a reference to the remaining bytes that are going to be needed for decoding later on. So as an example, I'm going to implement this trait here on, let's say, an integer. I'm going to create our error type. What am I doing? So when we encode this type, we're going to want to convert it to a representation that's quite portable. So integers have a property known as endianness on modern architectures, and endianness is where the order of the bytes may change depending on the CPU that you're running it on. And of course, we want this to be consistent across architectures, and so we're going to want to decode this let me backtrack a moment. We're going to want to encode this in an endianness that is consistent across architectures, regardless of the endianness of the architecture. So we can do self.toLE bytes. So this is little endian bytes, and this is a consistent ordering. And then we can do actually, I think there's a better way of doing it. I'm just checking the chat now. My computer's really struggling with running OBS and YouTube at the same time. Yep. N times M problems are really difficult to solve in computer science because they don't appear that often, but when they do, the only way to disentangle them is to be really cautious and careful about how you design the API that links both ends together. Because if your API doesn't have the correct features, it may not support all of the combinations that you want. But if you add too many features, it becomes more difficult to implement and requires more boilerplate code to implement, which is basically is basically removing the whole point of it in the first place, right? Because you want to reduce the amount of code you have to write. So there's a bit of a knack to really carefully disentangling things and working out where the principal points of your API are and what you need to glue together and how. Here we go. I've just not used this much. We can use extend from slice, and then we can take the array of bytes as a reference in order to turn it into a slice. So now we've encoded our I32 as a series of bytes in the buffer, and now we want to decode it. So and actually, we need to be more specific here, because this byte slice here is a subslice of this slice here. Because if you imagine, for example, we have a series of bytes. Let's say that these are all bytes, for example, and we decode our I32, which requires 4 bytes. So we pass in this byte slice, and we remove the first 4 bytes. We go, okay, right, we've got our integer now, and we want to pass out again the remaining bytes. So the lifetimes of both of these are tied together because they're effectively the same thing, just with part of it cut off. So to do that, we're going to add a lifetime parameter that allows us to tie the lifetimes of these two together, like that. And this is in theory quite a fast way of deserializing things like this. So there are a few things we need to take care of here. It's going to be a little more complicated than encoding. Excuse me, I need to sneeze. Excuse me. Right. So first of all, we're going to want to check that the length of the byte slice is long enough for us to get our 4 bytes, okay? So I could just do something like if bytes.len is equal to 4, then we decode, and otherwise we produce an error. But as is usual, lifetime addition. So the compiler can do lifetime elision with a self parameter. I don't think it's able to in this case. That may have changed recently, but I'm pretty sure it still doesn't. Assume that those two lifetimes are bound together. I can give it a try in the Rust playground, actually, see if that works. Wow, my browser's being really slow with OBS running. Right, let's see. Okay, so it does work actually. I'm pretty sure that's new. I don't recall that having been the case until maybe a few months ago. So in that case, we can remove this lifetime, and the compiler will work it out for us, which is nice. So instead of just checking the length and then attempting a decoding, which will effectively mean checking the length twice, we can use a useful method called split at. So let me just check to see if there's a better way of doing this. I would have thought that split at would check its parameters, but apparently that's not the case. So what we might want to do actually is do something like this for now. We can do so the tail is the remaining bytes, and the head are the first 4 bytes that we want. So in the error case, we want to return an error, which is I32 error not enough bytes. Now we can create that error there. So the thing we're going to want to do first is to do I32 from LE bytes, and then we're going to want to put the bytes that we need in here. We're going to do we're going to attempt to check whether let me think about this. Is that the best way of doing it? Right, so what I'm going to do, I'm going to change up this method a bit. By using some combinator magic. Actually, that's spelled incorrectly. right there. So what this does here is it attempts to convert the byte slice into enough bytes, and if it does, and if it's a success, then it converts those bytes from little endian form into the I32, and then if that fails, it returns the bytes. But there's a small change we need to make here, which is that we also want to return the tail of the bytes. So we can do that like this. So we're returning the tail here. So this is how you might implement an I32, or rather an I32 as a form of data. We can also extend this for things like a hash map. So when we're storing information about the ledger diff, so how the ledger changes between milestones, we usually have I've lost my train of thought again. I apologise, I've been a bit ill today, so I'm not very on top of things. So with a hash map, right, yeah, a hash map. So we're using a hash map to store all of the differences in the ledger address values. So we'd want to encode that as a piece of data by going through all of the hash map entries and encoding them each. And if we, for example, store the account balance with a number like this, then we can just use the implementation of this recursively in order to turn all of our bits of data into a byte buffer. So you may notice that this is fairly similar to how CERD does things, but the difference with CERD is that it doesn't really deterministically produce certain outputs. So, for example, the typical crate that you might use is bin code, which is used to serialize things to binary, but the format it produces is liable to change, and we want a deterministic format for the database, because, for example, we don't want the format that bin code understands changing and us decoding incorrect information from the database, because that would be quite clearly bad. So we're implementing things in this way in order to keep them deterministic. I think there are a few more changes that need to be made to this. I did more of a prototype yesterday. It had a few more features to cover some more cases, but hopefully this gives you a good idea of how we can use traits to kind of abstract the database backends and the data items themselves, and then you can reduce the n times m problem to an n plus m problem, and you can do that by disentangling them and making a common interface between both. Apologies if it was a bit of an ad hoc live stream. This is still a thing where we're in discussions about and is quite ongoing, and how we're thinking about doing things. Does anyone have any questions? Any questions? I'm going to presume not. Right, so we're pretty much at the hour. I don't think we really have enough time to go into anything else that's big. I hope you enjoyed this live stream, even if it's maybe a bit confusing. I get that a lot of this can seem quite abstract because we're not really showing these traits being implemented, which is the bit where all of that understanding of how they attach to the database backend and to the rest of the B types, will kind of fall into place and make more sense. But yeah, for anybody that thinks that well, Rust doesn't have inheritance, so it can't be used to make effective abstractions. Well, it can, and the trait system is a brilliant and dynamic way of doing it. And if you're new to Rust or you've not heard of it, I really recommend giving it a go. Okay, I think I'm going to end it here. Thank you all for watching. Have a nice weekend, you too. Bye.